Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into permutations.
Permutations?
Yeah, so how many different ways can you order a set of things? And this isn't just, some theoretical problem. This is something that pops up in coding interviews all the time.
Yeah, absolutely. And it's one of those problems that seems deceptively simple at first.
Right.
But it's a great way to illustrate some really core algorithmic thinking and, especially backtracking.
Okay, so let's set the scene for our listeners. Imagine, I hand you a bunch of different colored blocks, like red, blue, green, yellow.
Okay.
How many different ways can you arrange those blocks in a line?
Well, it depends on how many blocks you're giving me.
Okay.
So if you just give me one block, well, there's only one way I can arrange that.
Right.
But if you give me two, now I have two options, right? I can do red, blue, or blue, red.
Okay.
If we add a third block, then the possibilities really start to multiply.
Multiply. That's the right word, isn't it?
Yeah.
That's where the factorial comes in.
Exactly. So factorial is, represented by that exclamation mark.
Right.
And, essentially it means that you're multiplying a number by all of the whole numbers less than it all the way down to 1.
Okay.
So 3 factorial means 3 times 2 times 1, which gives us 6. If we have 4 blocks, that's 4 times 3 times 2 times 1, which is 24. So you can see how it really explodes.
So the factorials explain why, this problem gets so tricky so fast.
Exactly.
So with just a handful of items, the number of permutations just blows up.
Mm-hmm.
So if we were trying to code this up, like just listing out every single permutation manually would just not be practical at all.
Yeah, so if you try and brute force it, that might work for really, really small sets.
Right.
But as that, set size increases, it just becomes really, really inefficient.
Right.
Imagine you're trying to list out all the permutations of the letters of the alphabet.
Yeah, your computer would be like, no.
It would be crunching numbers forever.
So brute force is out the window. What's a more elegant way to handle this?
So this is where we bring in our star of the show, which is backtracking. It's a really powerful algorithmic technique for solving all kinds of problems.
Okay, backtracking. I remember hearing that term before.
Yeah.
Didn't we use that when we were talking about solving Sudoku?
Exactly. It's the same idea. Imagine you're exploring a maze, right? You make a choice, you go down one path, and if it leads to a dead end, you have to backtrack to your last decision point.
Right.
And then you try a different path, and it's a way to kind of systematically explore all the different possibilities.
So how does that apply to permutations?
Yeah.
I'm having trouble seeing the connection here.
So let's think about it as building a permutation one step at a time.
Okay.
We have our set of items, and we need to choose one item for the first position and then one item for the second position.
So it's like we're filling in slots one by one.
Exactly. We're filling in slots.
Okay.
But what if we make a choice early on that ends up leading to an invalid permutation, right?
Right.
Like if we're arranging those blocks and we put the same color block twice in a row, that's where backtracking comes in. We'd have to undo that last choice.
Right.
Go back a step and try a different option.
So we're being very careful in undoing our steps.
Right.
Whenever we hit a dead end.
Exactly.
That makes sense. But it seems like it could involve a lot of copying data around.
Right.
As we build these different permutations. So is there a way to make that more efficient?
You're thinking ahead. There's one key optimization that we can do, and that's swapping. So instead of creating a whole new array for each permutation,
okay,
we just swap elements within the original array.
Hold on, swap it. Can you explain that a little bit more?
Yeah, imagine you have your blocks all lined up in a row.
Yeah.
Instead of taking a block out and putting it in a new position, you just swap its position with another block.
Oh, so you're just rearranging the blocks within the same space.
Exactly.
Oh, that's cool. It's like shuffling a deck of cards rather than creating new decks for every single arrangement.
Exactly. It's very efficient.
Okay.
Especially when you have a lot of items to work with.
So this is where it gets really interesting. We have this backtracking approach.
Yeah.
Right? And now we're making it even smarter with this swapping.
Yeah.
But before we get too deep into that, I am curious, about the overall efficiency of this method.
Okay.
How does this compare to that scary factorial growth we were talking about earlier?
That's a great question. And it leads us into this concept of time complexity, which is, how long does it take an algorithm to run?
Right.
And even with backtracking and swapping, we still have to generate all possible permutations.
Right.
And the number of those permutations is that factorial.
Right.
So no matter how clever we are, we can't completely escape that factorial growth.
So even with the best algorithm in the world, it's still going to take a while to generate all the permutations of a really large set.
Yeah. But we can optimize our algorithms to make them as efficient as possible.
Right.
But there are these inherent limits that we just have to be aware of.
Okay, that makes sense. We're not performing miracles.
Right.
But we are, finding the smartest way to navigate this complex world of permutations.
Yeah.
So we've got the why of backtracking, but how do we actually code this thing up? That's where it gets really fun.
Yeah, let's get into that. So in part one, we established that, backtracking with swapping is the way to go for efficiently generating these permutations.
Right.
So now let's imagine how we'd actually tackle this, if we were to code this up.
Okay, so we're putting on our programmer hats.
Exactly.
We have this concept of backtracking in mind, but where do we even start translating that into code?
So I think the key is to break this problem down into smaller, more manageable steps, right?
Right.
So we need a way to keep track of the permutation that we're currently building.
Okay.
We need a way to know which elements we've already used.
Okay.
And we also need a way to kind of back up if we hit a dead end, right? Like we were talking about.
So we need some kind of storage to hold the permutation that we're currently building, like maybe a list or something.
A list would be a great way to do it.
Or we just add elements one by one as we go.
Think of it as your workspace, right?
Oh,
As you're making these choices about which elements to include, you add them to this list.
got it. Okay, so that makes sense. But how do we keep track of which elements we've already used?
So we could use a Boolean array for that.
A Boolean array, what's that?
So a Boolean array is just an array where every element is either true or false.
Okay.
And each element in that array corresponds to an element in our original set.
Okay.
So if an element's already been used in our current permutation, we mark its corresponding entry in that array as true.
So it's like a checklist.
Exactly. It's like a checklist.
Okay, much better than my messy whiteboard with crossouts and stuff.
Yeah, exactly.
Yeah.
So imagine we're, deep in this process, we're building a permutation.
Okay.
We've made a few choices.
Uh-huh.
And now we need to figure out what the next element should be, right?
Right.
How do we make that decision?
So picture me staring at this list of elements, trying to decide what goes next.
Yeah.
How do we even approach that?
So this is where that backtracking logic really comes in.
Okay.
We iterate through each element in our original set, right?
Okay.
And for each element, we check two things. Is it already used in the current permutation?
Okay.
And does it meet any other constraints of the problem?
Constraints. What do you mean by that?
Yeah, so imagine we're generating permutations of numbers, but we only want permutations that are in ascending order.
Okay.
Right, that's a constraint.
Right.
So when we're considering an element to add to our permutation, we need to make sure that it's larger than the previous element that we added.
Okay, so those constraints can really, shape the possibilities here.
Exactly.
So let's say we find an element that's both unused and it meets the constraints. What happens next?
We add it to our current permutation list.
Okay.
We mark it as used in our Boolean array.
Right.
And then this is the key part. We dive deeper.
Deeper, what do you mean?
We essentially repeat the process, but now we're looking at the next position in the permutation.
Okay.
Right? So we ask the same questions, which elements are unused and meet the constraints.
Okay.
We make a choice, we add it to our list, and then we dive deeper again.
So it's like a recursive process.
It is. It's a recursive process.
We keep making choices and going deeper until
we hit the end, and
Yeah.
the end is when our permutation list has reached, that desired length that we want.
Okay.
So at that point, we've successfully generated a complete permutation.
Right.
So we add that to our collection of results, and then this is the backtracking step we back up.
Okay, backing up. So we're going back in the maze.
Exactly. We're retracing our steps.
Right.
We remove that last element that we added.
Right.
We mark it as unused again in our Boolean array.
Got it.
And then we're back to that previous decision point and ready to explore other possibilities.
That's clever. Okay, but remember that swapping trick we talked about earlier?
Yeah.
How does that fit into all of this recursion?
That's the beauty of it. Instead of actually adding and removing elements from a list, we can actually just swap them within the original array.
Okay.
So before we make that recursive call, we swap the element at the current position with the element that we want to add. And then after that recursive call returns, we swap them back.
Wait, so we're manipulating the original array directly?
It's like a temporary rearranging.
Okay, so we're swapping just to kind of put things in place temporarily.
Yeah. We swap them to put that chosen element in the current position, and then we swap them back to restore the original order.
So it's like a temporary assignment, like, hey, you're in charge for now, but then you go back to your original spot?
Exactly.
Yeah.
And this swapping approach has a big advantage. It's really efficient in terms of memory usage.
Right, we're not creating like copies of this array
No, we're just rearranging things in place.
over and over again. Okay, I'm starting to see the beauty of this approach.
Yeah.
We have this systematic exploration of backtracking, right? Combined with the efficiency of swapping. We've essentially created like a lean, mean permutation generating machine.
That's a great way to put it. But remember, even with all these optimizations, right, we're still bound by that factorial time complexity.
Right.
The number of permutations can get incredibly large.
Right, so even with the best algorithm in the world, it could still take a while to generate all the permutations for a large set.
Yeah, that's an important point to keep in mind. Optimization is all about finding the best possible approach within those inherent limits.
Okay, that makes sense.
And sometimes the best approach might still not be fast enough for certain situations.
Right, so we've talked about backtracking, we've talked about swapping, we've talked about, this concept of time complexity, like where do we go from here?
Yeah, let's dive into that.
Welcome back to AI.Code.Cast for the, final part of our permutation deep
The
dive.
grand finale.
We've covered a lot of ground from, understanding the problem to exploring the elegance of backtracking with swapping.
We've been through a lot.
But I have a feeling there's even more to uncover here.
Absolutely. There's always more, right? We focused on one really powerful technique, but there are other approaches out there.
Yep.
And, each approach has its own strengths and its own trade-offs. So it's like having different tools in your coding toolbox.
Okay, I'm all ears. What other tools should we be adding to our arsenal for tackling permutations?
Let's start with a technique that might surprise you using built-in functions.
Built-in functions.
Yeah, so some programming languages actually provide, handy functions that can generate permutations for you.
Oh, wow.
So, for example, in C++, there's a function called next permutation.
Built-in functions, that sounds almost too easy. Less code for us to write.
Exactly. But there is a catch. They often come with specific constraints.
Okay.
So next permutation, for example, generates permutations in a particular order called lexicographic order.
Lexicographic order, that sounds familiar. Is that like alphabetical order?
Yeah, you got to imagine arranging words in a dictionary. That's lexicographic order. And with numbers, it means, starting with the smallest possible permutation and then systematically generating the next largest one, and so on.
Okay. I can see that. So this next permutation function takes an array and just magically rearranges it to
Right.
give us the next permutation in that lexicographic sequence.
Exactly. You don't have to worry about all the intricacies of swapping or backtracking. It
Yeah.
just handles it all behind the scenes.
That sounds like a time saver for sure, but there must be some downsides, right? I mean, if it were that easy, everyone would just use built-in functions all the time.
You're right. There are some trade-offs.
Okay.
First of all, these functions might not be available in every programming language.
Right. If you're working with a language that doesn't have a built-in permutation generator, you're back to implementing your own solution.
Exactly. And, think about what we've been discussing. What if you don't need all the permutation?
Right.
What if you only need a certain subset, or you want to apply some custom logic during the generation process? These built-in functions might not give you that level of flexibility.
Ah, so it's kind of a double-edged sword. It's super convenient if you just need, all the permutations in a specific order, but it might not be the right tool for more specialized scenarios.
Yeah, exactly.
Okay, so we've got built-in functions. What other approaches are out there?
Let's switch gears and talk about a technique that involves a stack.
A stack, like a stack of pancakes.
Okay. Maybe not pancakes, but you've got the right mental image.
Okay.
A stack is a data structure that follows this, last in, first out principle.
Okay.
So think of it like a stack of plates. You can only add or remove plates from the top.
Okay. I'm visualizing this stack of plates now, but how do we use that to generate permutations? It seems like kind of a leap.
Here's the key insight. A stack allows us to simulate those recursive calls of our backtracking algorithm,
Right.
but in an iterative way.
Wait, iterative. So no more recursion. Why would we want to do that?
There's a couple of reasons.
Okay.
First, iterative solutions can sometimes be more memory efficient than recursive solutions. Especially for problems that involve lots of recursive calls. You can imagine a really deep recursion, like trying to find all permutations of a very large set.
Right.
That could lead to what's called a stack overflow error, literally.
Ah, so we're trying to avoid those computer crunching scenarios.
Exactly. And the other reason is control.
Okay.
Iterative solutions give you finer-grained control over the execution flow, right? You can introduce optimizations or modifications that might be trickier to do with recursion.
Okay, so it's all about those trade-offs. Again, recursion is often more elegant and easier to understand, but iterative solutions using stacks can offer those performance and control advantages in certain situations.
Exactly. There's no single best approach, right? The right tool for the job depends on the specific problem, the
Yeah.
size of the data,
Right.
and even your own coding style and your own preferences.
Well, this has been an incredible journey. We've explored the world of permutations from multiple angles, learned about backtracking, swapping built-in functions, even stacks.
It's been quite the adventure.
My mind is buzzing with all these new concepts.
That's what we like to hear.
So folks, that wraps up our permutations deep dive. We hope you've enjoyed exploring this fascinating corner of the coding world with us.
Absolutely. Remember, the journey doesn't end here. Keep experimenting, keep learning, keep pushing those boundaries of what you can create with code.
Well said. Until next time, happy coding.